Okay, as usually, let me check the sound, okay, to make sure we have it. And okay, here we go. Let's do the number 9. Question number 9. And basically on number 9, we got here a buffer. I already went through the buffers, okay? And we look at the equation in which we can find the pH of a buffer using this. pH is equal to, hold on, pH equals to 2 pKa plus the log of the concentration of the conjugate base, this is in general, divided by the concentration of the acid, weak acid. Let's double check the equation to make sure we're doing it right, and also you can see it. Okay, here it is. Yep. There's another one too. You can use it like the concentration of hydronium. You can use the minus the log, but it has to be flipped. The acid on top and the base on bottom. Any one, it's okay. This one, I like it because it's the Henderson-Hasselbalch equation. Like it, I like to use it. Okay, so this is an easy exercise, fast. And it's the pH of a buffer. So we need to find out that. We have already the pKa, and we're going to plug in we're going to solve it for the pH. So what is the pKa? It's 10.0. 10.00, okay, plus the log, and the concentration of the conjugate base would be this one, okay? Ionic, C6H is the phenyl. Okay, it's C6H5. And in aqueous solution, this dissociates into C6H5. O negative plus Na. So we have the conjugate base present. So this is going to be the concentration, the log of the concentration of the conjugate base, which is 1.1 molar, divided by 1.3 molar. We usually don't use the units because they cancel out here. So let's put it a little bit on bottom. We got it here. So the pH would be equal to, I'm going to break it down. First, second problem, then directly, plus the log of, what is the concentration of that? 1.3. So 1.3, we are on problem 9. I don't have it here. I have it directly. 9.9, 1.1 and divided in 1.1 divided by 1.3 gives me 0.846. 0.846 to 0.8462. And if we get the log of this, it's going to be pH equals 10.00, and the log would be minus 0.07255. Okay, or pH would be, as we only have two decimals, two decimals with the pH. Okay, don't forget that because that happened the other day. 0. During the test. 72. 10.00, 10.00 minus 0.07 gives you 9.93. And that's the answer I got. Okay, so the pH would be 9.93. Let's go move forward. Okay, let's do 10. All of them are very similar. So the pH would be pKa 3.74. You see? I'm going to plug in, I'm going to put all the values first, minus the log directly, because the formula probably by now you should know it by memory. Goes to 0.28, okay, which is a conjugate base, divided by 0.60. Again, this is less than 1, so the pH should be less than the pKa. So the pH would be equal to 3.74 plus the log of this. This is 0 point minus, because it's a negative, 0.33. pH would be equal to 3.41. You see, these problems are easy and short. There's going to be a lot of other problems that are a pain. Okay, here again, pH. Now, here we got a base. Okay, and we're going to do, instead of doing the pH, the same thing but with the pOH. Okay, let me write the equation, which I wanted you to do it on the test. And it's going to be NH4 plus A3O OH minus. The hydrogen gives the hydrogen. The water gives the hydrogen to the proton, and then you have conjugate acid. So now the conjugate acid that you have present in a buffer would, as honest, I will go back to the base. NH3 plus H2O. Mm-hmm. No, I'm sorry, H3O. You lose it acts like a acid. Okay, now I got it. So the now we're going to find the pOH, which is going to be the pKb here. pKb of ammonia would be, I'm going to get it from here, 4.75. You look at the problem, you're going to have it there. You see? Plus the log, the same thing, but now on top is going to go the conjugate base acid of the base. It always goes the conjugate on top. So it's going to be 0.15 divided by the base. Before we had the conjugate base of a weak acid. Now we're going to put the conjugate acid of a weak base, which is ammonia. So you got here 0.15 divided by 0.25. The pOH would be equal to 4.75 if you solve this side, plus this is going to be negative, plus negative, I did it directly, 0.15 divided by 0.25. You get the log is 0.6 of this. Is going to be minus 0.222, which is going to be POH is going to be 4.75 minus 222. POH is going to be 4.528 or 4.53. And if you subtract from 14, remember pH plus POH gives you 14 equal to 14. So pH would be 14 minus 4.53. So pH would be 9.47. A base. Now, if you look at the ones we've done here, see how the pH changes when you have present, of course, the conjugate base. And that also happened, let's see, with the acid, look at the pH. If we didn't have that, we'd have to work with the Ka only. And let me do something here to show you something. Okay, I'm going to show you something. I did the math, so this over here, this is the pH, okay, of the buffer, right? Of the buffer solution with a weak acid and its conjugate base, 3.41. If we do the acid by itself, formic acid, the Ka of formic acid is 1.8 by 10 to the negative 4. And we do the ICE table. So we take a look, we go ahead and find the X, which is the concentration of hydronium, and it gives us this. That's what I did when I was, gives us this. Okay, so I did cross out the X, but I verify and it's less than a 5%, so I can do that. It's valid, my assumption. And then look at the pH that I got, 1.98. So if I do the pH by itself, the acid by itself without the conjugate base present, the pH is much lower, meaning that you increase the pH of a buffer. Do you see? Because we have present the conjugate base. I don't know if it makes sense for you guys, but that's a way also to express it. So we got here 453, and that is the 11. We're going to do 12, but I have it in another one, so... Okay, let's look at it. 12 would be the same as 11. It's finding the POH with the base, the same we did it. Is the POH and then finding the pH by subtracting to 14. So then let's go with the 13. Okay, this 13 is a little bit more of a pain. And basically what we have is ditropic acid, which is the carbonate, H2, write the equation, CO3 plus water, the ionization equation. It gives me carbonic acid, it gives me HCO3 negative 1 plus the hydronium. Now the second one, this would be Ka1. The second one would be the H2, the conjugate base, second ionization, negative plus the water again, gives me CO3 negative 2 plus water. Plus hydronium, sorry. Now this would be the Ka2. And in asking which one is more important, now I want you to see that this is the conjugate base of this acid, acting as an acid, which is a conjugate base of a carbonic acid, but it's acting as the conjugate base, acid, sorry. The conjugate base is acting like an acid. And CO3, guess which one is more important? If they give me the concentration of CO3, -2, that's a conjugate base, and they give me the concentration of KH, which this is going to be HCO3 -1, the most important one would be the Ka2, because that's what we're going to be working with. To find the buffer, we got a weak acid plus its conjugate base. So the value we want to calculate the pH is the pK2, this one, of this one. Okay, so the first thing here is finding the pK2, right? I don't know if you understood, but they're giving me this one and this one. So that's the most important one, so you choose this one here. So pK2 would be the minus the log of K2, which is 4.7 times 10 to the minus 11 pK2, because that's what we're going to use, equals the, hold on, 475. No, that's 11, sorry. The pK2 would be 10.33. 33. Now, looking at the equation again for the buffer and for calculate the pH of a buffer, let me write it down so you're sure why your pK2, K2 is the most important, because you got plus the log of what concentration is the concentration of CO3 -2, which is this one, you see, of the CO3 -2 divided by the concentration of this HCO3 -1. So we're going to have here pH equals 10.33 plus the log. I'm just going to write the expression and then the results of, let me show you, 0.68, this is a CO3, the base, and divided by 0.29. Remember, you're going to have different numbers, but you can do it here. So it's going to be 0.68, the molar, divided by 0.29. So if you solve all this, the pH is giving you, let me add them, 10.33. Now you got the higher on top, positive, so this is going to be a positive number, 0.37. Because this is higher than this one, this is going to give you greater than 1. The plus log gives you a positive number. So the pH is going to be, in this case, 10.70. If you got the same numbers, you're lucky. If you got a different one, it's okay, because you know how to do it. Okay, let's go with the next one. 14 would be 14. Did I pass it? No. Okay, again, okay, it is, you got phosphoric, which is 3. You got Ka1 is the H3PO4. I'll put it on the left this time. Plus water, we're going to do the ionization of each of them, gives me H2PO4 conjugate base. Okay, -1 plus, I lost 1 proton, 1 hydrogen, plus. Then you got Ka2 would be the second step, the conjugate base of phosphoric acid, H2PO4, and then we lose the second one, the next step, and it's going to be HPO4 negative 2 plus H3O plus. And then finally, Ka3 would be HPO4 negative 2 plus water gives me the PO4. I know it's a pain doing all this, but we have to. Negative 3 plus H3O plus. So now we get and say, okay, what are the values they're giving me? They're giving me these two. Okay, which here, if you look at this, this is the HPO4 negative 2. But which one is this? This one. So what is going to be the most important? They're giving me this one. And look at the other one they're giving me, HPO4. So the most important again is the 2. Coincidence, but it's the way it works. Okay? Most important is the 2. Because those are the ones we're going to use. Now pH would be the same thing. pH would be the pKa of what? Of the second one. Plus the log. And which concentration, which is the conjugate base and the acid, would be HPO4 negative 2. The concentration, which is 0.34. And the concentration of the acid would be, which is the H2PO4 negative 1. That's the second step of ionization of phosphoric acid. So the pH would be, okay, the Ka2 gave me 720, the pKa, plus the log of, on top goes, on top goes 0.34 divided by the acid 0.20. In this case is 0.34 divided by 0.20. The log of this, we do and solve for this, so it's going to be 720. This is going to be positive, and this is going to be 0.23. And this is going to be 7.43. That's the answer. Let's go to the next one. That's the 15. And the 15 is, they give you the pK and the pH. So if you use for nitrous acid, HNO2. So you got the equation plus water. Whoops, too big, but I was going to do it's the NO2 negative plus the H3O plus. So here we got that the ratio is this one divided by this one. So the pH would be the pKa of this nitrous acid plus the log of the concentration of NO2 negative divided by the concentration of HNO2. So if we use this, let's get all the number. We got the pH 2.47. You see? 2.47. The pKa, the Ka is 7.1. So if we got the pKa, the minus the log of the Ka, gives me, I'm going to give it to you directly. It's giving you 3.15. 3.15. That's the pKa. So here goes 3.15 plus the log of this ratio of the conjugate base divided by the concentration of the acid. So this is the whole thing what we have to find. You can call it X and solve it like that, or you can leave it there. So I'm going to call it X. 2.47 equals 3.15 plus the log, and this I'm going to call it X. Okay, so you want to subtract this, you want to take this to the left. 2.47 minus 3.15 equals the log of X. Okay, after we find this, then this is minus 0. That's a number I got, 6787. Well, it was longer. Equals the log of X. And if you want to find out the value of X, which is this ratio, is going to be e to the minus 0. That's why I did it with the n instead of equals. Then you eliminate, it would be X. Okay, and X gives you 0.2095. And they use two sigfigs coming from the constant. So X is the ratio between the concentration of conjugate base divided by the concentration of the acid. You remember this, right? I got it from here. I put X so just to simplify. So that means that this ratio equals 0. And they use two sigfigs, 21. Okay. Now, before we go to the long ones, the last one here, the next one, would be 16, which is the same as 15. It's the same. So if you know how to do 15, you can do the 16. Let's look at the time for a second.